Hello, everyone. My name is Nasser Razavi. Today, I'm going to present the Machine Learning for Green Energy Demonstrator project. In this presentation, I'm going to start by giving you a brief introduction of the project. Then I will talk a bit about the machine learning techniques we use for this project. Finally, I will run the demonstrator and try to explain its main features and functionalities. Before that, let me introduce the team members. This project is led by Anthony Faustin and I under the supervision of Ocean Boydell. I would also like to grab the opportunity to give a special thanks to the companies involved in this project. Okay, why we do need machine learning on smart meter data? Nowadays, smart metering is becoming an integral part of smart grids. As a result, significant quantities of smart meter data are being produced every day. By applying machine learning on this data, we can extract useful knowledge and create value-added services. And in line with that, the goal of this project was to develop and test machine learning approaches to extract relevant insights from smart meter data that contributes to higher energy efficiency levels. In the past few years, there has been plenty of research and work on the application of machine learning on smart meter data in the areas like load disaggregation, load profiling, load forecasting, load management, and anomaly detection. But for the purpose of this project, we focus only on load profiling and load forecasting. Load profiling can be used in scenarios like customer segmentation, eco feedback, and targeted customer engagement program. Similarly, load forecasting can be used in other scenarios like managing demand, load profile prediction, and price prediction. Okay, for the first part of the project, which is load profiling, we use the clustering method called improved deep embedded clustering, or IDEC for short, which is based on autoencoders to extract deep embedded features in a very low dimensional space. We then use that compact set of features for clustering users based on their energy consumption patterns. When you are working with high dimensional data, first you need to reduce the dimension by mapping data from its original high dimensional space to a lower dimensional space. Otherwise, clustering becomes ineffective due to unreliable similarity measures. Another option was to use dimensionality reduction methods such as principal component analysis, or PCA, and following that, apply a simple clustering algorithm such as k-means to cluster the low dimensional data. However, the problem with such approaches is that PCA relies on linear relationship between features. But what if there exist nonlinear correlations? To be able to compare the result of these two clustering methods, as you will see, we have implemented both of these methods in the demonstrator. You will see in a minute. And for the second part of the project, which was about forecasting the total demand, we have used a probabilistic machine learning model called state space model. The probabilistic aspect of this model produces a Gaussian probability distribution over the possible output as opposed to a single value. I will explain more about it when running the demonstrator. It's worth mentioning that we tried other models such as neural networks, but this model had better result in terms of prediction accuracy. So in summary, in the machine learning for green energy demonstrator project, first we use a deep learning approach to perform automatic feature extraction and clustering load profiles at the same time. We then use the deep embedded clustering result for total demand prediction for each cluster using a probabilistic model. Okay, now let me show you the demonstrator page. Okay, you see the homepage of the demonstrator, and now I talk about its feature and how it works. Okay, at the top of the page, you can see general information about the demonstrator, such as introduction and some information about the clustering and forecasting method that we use in the project, as well as some information about the data set. For example, you can see here the data set. As you can see over here, for this project, we have used a public data set called London Smart Meter Dataset, which contains half-hourly smart meter measurement for a sample of over 5,000 London households. These measurements are collected between November 2011 and February 2014, but we only use the data from 2013 because the data from the previous years had a lot of missing values. For the purpose of this demonstrator and for performance reasons, we split the data into 12 different files so that each file contains only the data for one specific month in 2013. Okay, now before running the demonstrator, let me explain the input options. First of all, here you have a menu from which you can select the data for a specific month. You can select any month you want in 2013. For a better understanding of the data, you can consider the data for each month as a table, having one row for each possible timestamp during the selected month and one column for each household. Since the measurements are taken at 30 minutes intervals, if we assume that there are 30 days in a month and we multiply this by the number of readings per day, which is 48, we will get the number of rows, which is roughly 1500. After selecting the month, you have to specify the number of clusters as it is required by both k-means and IDEC clustering algorithms. However, if you are going to use k-means, by checking this box next to the number of clusters, you can ask the demonstrator to calculate the number of clusters using the elbow method. If you want to know more about this method, you can follow the link provided in the description part of this page. Okay, once you have specified the number of clusters, you can choose one of the two clustering methods provided here. You can choose either k-means or IDEC. By choosing IDEC, you can expect to see better clustering compared to k-means. But please keep in mind that by selecting IDEC, you have to wait a few more minutes to see the result. And this is because of the training phases needed to train the autoencoder model. Finally, the last option is only for visualization purposes. In this project, instead of clustering raw data in the original feature space, which, as I mentioned, comes from a very high dimensional space, like 1500 in our case. First, by using the autoencoder, we map data to an embedding space with a very low dimension, like 10. And then we run the clustering on the embedded low dimensional data. As I mentioned earlier, clustering methods become ineffective for very high dimensional data due to unreliable similarity measure. But even after mapping data to a 10-dimensional space, we still will not be able to visualize the data and resulting clusters. To overcome this issue, we have used the t-SNE visualization tool to visualize high-dimensional data in 2D space. So this tool will help you have a better understanding of the resulting clusters, as well as compare the result of these two different clustering methods. Now, after configuring the value of the parameter, it's time to run the demonstrator. But since it takes a few minutes to run the demonstrator, I am going to show you the result from previous runs. Let's take a look at this specific run. As you can see here, you can see all the values selected for this specific run. For example, we have selected the first month of the year, and we have set the number of clusters to 10. Also, we have used clustering method IDEC, and we check the box for t-SNE visualization. Now let me show you the result page. The first part in the result page is related to the clustering, and the second part at the bottom of the page here is related to the forecasting. Okay, as you can see here, we have 10 clusters which are sorted based on the percentage of the data belonging to each cluster. For example, the first cluster contains almost 28% of the data, and the second cluster contains almost 18.5% of the data. Since the clusters are sorted, you will see the most common energy consumption pattern at the top. And as you go down, you will see less common patterns, which you might want to consider as anomaly cases. Now, if we look at the very first cluster here, we can see numerous black lines and one red line within the graph. These black lines are the daily consumption patterns averaged over a month within each household. And the red line shows the average consumption pattern of the entire cluster. As you can see in the first few patterns here, households tend to consume minimal amounts of energy throughout the night. However, later throughout the day, we can see a gradual increase in energy consumption while peaking at dinner time. This pattern seems to be the normal energy usage pattern for almost 90% of the households. This application of clustering also highlights some more interesting patterns in energy consumption throughout the households. For instance, when we take a look at cluster 8 over here, we see a maximum energy consumption rate at nighttime, which might be related to a storage heating overnight. Also, we might find more interesting patterns when running the demonstrator on other data sets. Also, we are able to observe and speculate ideas around these patterns. Further research and expertise is needed to analyze and understand this data. In summary, this type of clustering can be considered as a valuable tool to discover different energy usage patterns or to identify the most common usage patterns as well as the least common usage patterns, or to identify those clusters that are potentially more profitable for the utility, or maybe to try shift the load with the hope to provide the cheaper prices. Okay, let's move on to the next part. In the next part here, we can see the result of the T-SNE visualization to take a look at the clusters into the space. Using the IDEC method, we can clearly see compact clusters that are well separated from each other. If we were to go back and look at the exact same data, but using k-means, let me show you, for example, here. The only difference is in this round, I have just used k-means instead of IDEC. You can see a more chaotic distribution of the clusters overlaying on one another. And finally, let's move on to the last part where you can see the total demand forecasting for each cluster. In each graph here, the black line shows the true value and the red line shows the model prediction. Also, the red margin around the red line, the red margin around the red line shows the probability distribution at each specific timestamp. A wide margin shows that the model is less certain about its prediction, and a narrow margin shows that the model is more certain about its prediction. Here to train the model, we have used the first 3 weeks of the selected month for training and the last week for testing. So all these graphs are showing the prediction for the last week of January in 2013, as you can see here. Okay, in most cases, the predictions are pretty accurate. However, for clusters with a few number of samples, we expect less accurate predictions. In this demonstration, we had about 5,000 samples in our dataset. But for real-world application with larger dataset, you can expect to get better predictions. Okay, now at the end of my presentation, I want to thank you all for gathering here and listening to this presentation. If you have any question, please feel free to email me at sayed.razavi@ucd.ie or ask me at the end of the event. Thank you.